In this video, we will discuss some general methodology and debugging strategies that can help you while you design and train your own neural networks. So let's get started.
General methodology for training neural networks. Okay, so first is what deep learning model should I apply? So this depends on your inputs and the task that you're trying to solve. If you have fixed size vectors as inputs, then you'd want to just use feed-forward neural networks, and it could be fully connected layers, but you can also have residual connections and so on. The main thing here is that convolutions and recurrent units aren't very helpful here. Whereas if you have inputs that have this topological structure, such as images, then for sure you would want to use convolutional neural networks. And in cases that your input is time varying, then you'd want to use, for example, recurrent neural network, probably with convolutions along the time dimensions or transformers. You will learn about transformers in the coming lectures. Finally, if you have a sequence of images or text or any other form of sequential input, then you would want to use LSTMs or GRUs, for example. Again, probably with a convolutional neural network. And also in this case, you can use transformers as well. Now let's look at some practical design considerations. First, you want to determine your goal and which performance metrics you want to optimize your model for. You shouldn't go create your model and start optimizing it for some random metric and then realize, oh, this is not the right metric for this task that I'm doing. So you should early on know about the standard metrics for different problems, especially for the problem that you're trying to solve, and then go optimize the performance of your model according to this metric. The second thing is to establish a working end-to-end pipeline as soon as possible. And the thing that you should not do here is to spend months on building your model with all the new techniques that you come across in papers, and then train the network for the first time after several months. So what you should do is to get your basic structure within a few days and then start training your network early on. It probably won't work out well for the first time, but maybe you get lucky. But most often what you do is this iterative refinement cycle where you add one component at a time and you keep monitoring the performance and you keep debugging it. In case things don't work out, then you reiterate this performance. So we will go more into how to do this debugging step in the later slides. So what you should start with, if your task that you're trying to solve is similar to something that exists, then maybe start with the architecture that has already been shown to perform well and with the right hyperparameters that have been shown to give a good performance. So there's lots of open source code nowadays, and you should start from something that's already been shown to work well. So another thing that you should do is transfer learning, as we saw in the previous video. So either from ImageNet or from any other model that's trained on a large scale data set that's publicly available, for example. And if you can't initialize the entire network with pre-trained weights from this other model, then what you should do is to at least see if you can initialize a few layers from this pre-trained model. And this really, really helps in practice. Then during development, you should determine what the bottleneck in the performance is. And you can do this by analyzing the training error, the validation error, and if you're overfitting or underfitting on this data. So you should see if you can get more diverse training data in case you find that your network is overfitting and so on. And you should also optimize the hyperparameters of your network when you do this. All right, so let's look at some debugging strategies. First is try to fit on a tiny data set. Then visualizing what the model does and what the worst mistakes are could be other strategies. Another thing that you should do is to monitor the histograms of the activations and the gradients. You should check if you have vanishing gradients or exploding gradients and so on. You should also monitor these things while your network is training. And in case you find that something is wrong, then you should find a solution for it and basically start training again. And you should do this in an iterative manner, we just discussed before. But let's first look at each of these in more detail. Okay, training on a tiny data set. So if the training error does not vanish on a tiny data set, then something must be really, really wrong. By a tiny data set, I mean in the order of 10 samples. So if you cannot get this training error to go down to 0, then something is definitely wrong. The things that you can check here is maybe you can see what is wrong in the code that you wrote. Maybe you are feeding the input data incorrectly or not in the right manner that the network basically expects. Or there could be something wrong with the optimizer such that the learning rate is either too low or too large. So this is the first thing that you need to get right. So if you can get this working on a tiny data set, then it's never going to work on the full large data set. So another way to debug is to just feed constant zeros at the input or random data as the input, which basically means something like a black image, and check if the output biases reflect the class distribution. This means that if you have an imbalance in your data set, let's say 5% positive and 95% negative, and if the inputs are zeros, then you want the softmax output to also be 5% and 95%. If this isn't the case, then you should go fix your output biases. So one important strategy is to also visualize your inputs. So maybe you have loaded the image incorrectly, or you have applied some bad data augmentation. So visualizing the inputs after any pre-processing or after any augmentation can be really helpful here. Another good strategy is to visualize the outputs of your model. If you only look at the metrics, it's often not enough because you don't really know in which cases your model is performing poorly. In the example that's shown here, let's assume that we do object detection and you visualize the output. Then, for instance, you find that your detector is always making these mistakes while it's trying to detect a person. Then maybe you can infer that your data set has fewer number of examples of persons, and then you can fix that. If your model is generating, for example, speech, then maybe you want to listen to the speech samples and see if you can find anything wrong with it. So there are also various other feature visualization methods such as TSNE or MDS, and this can also help you to further visualize the features that your model learns. So I'm not going to go into details into these feature visualization methods, but you can look them up when you want to do these while you're debugging. So this is also an important strategy, visualizing the worst mistakes. Here you see examples of recognizing street numbers from the Google Street View. So Google wanted to automatically classify house numbers so that they could have them annotated in Google Maps. What you see here is the mistakes that the model made. And we can see that for the most of these, the model performs reasonable predictions. Here you can see that the model predicts 184 instead of 1844. And this is because it looks like one of the digits has actually fallen off. And here in the next example, you can see that the network is actually supposed to predict 62-37, but the network only predicts 62 because the 37 is really only partially visible here. So these mistakes are quite reasonable. So if mistakes such as these are only a tiny percentage, then it's fine. But then you need to see that these types of mistakes are not a large percentage, say approximately 10%. Then you probably want to have an explicit way to handle this in your network. The last one is monitoring the histograms of the activations and the gradients. You should always monitor the gradient values and see if there's a vanishing or an exploding gradient. You should check if some activations are 0, then you can probably prune these activations and remove these units. By doing this, you can gain inference speed and you can also reduce the size of your model. Because when these activations are off, they're basically not doing much and these can be pruned off. All right, so this brings us to the end of this video, and I have 2 questions for you. If you have trained your network and you find that it performs really poorly in the quantitative metrics, how would you debug this? And if you have, let's say, an innovative idea for a completely new type of activation function or a layer, and if you want to implement it yourselves, which checks should you do to make sure that it works as expected? Now, I encourage you to pause this video now and to try to answer these questions, and we will continue in the next video. Thank you.